Hi all, welcome to new class. Today's class is about full wave rectifiers. In the previous class we have discussed about half wave rectifier. If you didn't watch it, please go through it. Let us go through the class. Full wave rectifiers are of two types, center tapped rectifier and bridge rectifier. So first of all, study the center tapped full wave rectifier. So this is the circuit diagram of a center tapped full wave rectifier. It consists of two diodes D1 and D2 connected to the center tapped secondary coil of a transformer and a load resistor RL. The primary coil of the transformer is connected to the AC mains. And notice that only one half of the total secondary voltage is used for each diode. Let V is equal to Vm sin omega t be the instantaneous sinusoidal voltage of frequency 50 Hz appearing across the secondary coil. The secondary voltage is split into halves. One half appearing across D1 in series with RL, the other half appearing across D2 also in series with the load resistor. And during the positive half cycle of the AC input. So during the positive half cycle, so let this terminal be A and this be B. So terminal A is positive with respect to B. So diode D1 is forward biased. So it will be acting as a short circuit. The current therefore flows through the diode D1 and voltage is developed across RL. So V out is across this RL. So during the positive half cycle, diode D1 conducts. So current will be flowing in this way and we get the output across RL and it will be like this. And during the negative half cycle, so this is the negative half cycle, the terminal A is negative with respect to B. So B is positive. Then diode D2 is then forward biased. Consequently, the current flows through the load resistor. So here the current flow will be in this way. So we get the output across the load resistor. So in the negative half cycle, diode D2 conducts, so we will get the output across the load resistor. Again in the positive half cycle, D1 conducts, so this is D1 conducts, this is D2. Next again D1 conducts. In the negative half cycle, D2 conducts. So in this way we will get the output. Next is peak inverse voltage. So peak inverse voltage is the maximum reverse biased voltage that appears across the diode during the negative half cycle. So when the diode D1 is forward biased, the voltage across the non-conducting diode, that is the voltage, this when diode D1 is forward biased, D2 will be in open condition. So maximum value of the voltage which appears across this D2 will be equal to the peak inverse voltage. So when D1 conducts, the voltage across the non-conducting diode D2, so D2 will be equal to the sum of voltage across the lower half of the secondary coil and the load resistor. So the voltage across the lower half is also equal to Vm sin omega t, and through the load resistor also equal to Vm sin omega t, because this diode conducts, and the maximum voltage is Vm. So across this coil plus across the load resistor, and that is equal to Vm plus Vm. So the peak inverse voltage across the non-conducting diode is 2 Vm, and that is equal to the peak inverse voltage in the case of center tapped full wave rectifier. Next is average values of output and load current. So the average or DC value of output voltage DC is area under the curve over a half cycle divided by base, and that is equal to area under the curve over a half cycle, means limit is up to 0 to pi, then V d theta divided by base is pi, and that is equal to integral 0 to pi Vm sin theta d theta divided by pi, and that is equal to Vm by pi is a constant, then integral 0 to pi sin theta d theta, and integral of sin theta is minus cos theta to the limit 0 to pi. Then applying the limit, we get Vm by pi minus cos pi. Cos pi is minus 1, so we get minus of minus plus 1, then minus of minus cos 0, that is minus of minus we get plus, then cos 0 is again 1, so we get 2 Vm by pi as the average value of output voltage. Also IDC is equal to 2Im by pi, and which is equal to 0.636 Im. Next is RMS value of load current. So IRMS equal to square root of integral over 0 to pi, because in the output voltage we have only the half cycles, that is, so here this is pi, 2 pi, 3 pi, 4 pi, etc. So to the first half cycle we have to consider. So here we get 0 to pi I square d theta divided by base is again pi, and that is equal to square root of integral 0 to pi I is Im square sin square theta d theta divided by pi, and that is equal to square root of Im square by pi is a constant, then integral of sin square theta. So sin square theta we can write 0 to pi 1 minus cos 2 theta divided by 2 d theta, and that is equal to square root of Im square by 2 is a constant, so 2 pi, then 1 minus cos 2 theta d theta, so integral of 1 is theta minus integral of cos 2 theta is sin 2 theta divided by 2 to the limit 0 to pi, and that is equal to square root of Im square divided by 2 pi. When applying the upper limit we get pi minus sin 2 pi is 0, then minus applying the lower limit we get 0. So Im square divided by 2 pi into pi, that is pi we can cancelled, and that is equal to square root of Im square divided by 2, and that is equal to Im divided by root 2. So IRMS is equal to Im divided by root 2. Similarly, VRMS equal to Vm divided by root 2, and that is equal to 0.707 Vm. Next is ripple factor. So ripple factor means the ratio of RMS value of AC component to the DC component. So we can write gamma is equal to square root of IRMS divided by IDC the whole square minus 1. So this equation we have derived in the previous class. So IRMS is Im by root 2. So Im divided by root 2 divided by IDC is 2Im by pi. 2Im divided by pi the whole square root then minus 1. So here Im square we can get cancelled, and that is equal to, so here we get pi square divided by 2 square, that is 4, into root 2 square, that is into 2, then minus 1, that is square root of pi divided by 2 root 2 the whole square minus 1, and which is equal to square root of pi square divided by 4 into 2 minus 1, and after solving this we get 0.482. That is, the ripple factor gamma is equal to 0.482 in the case of center tapped full wave rectifier. And in the case of center tapped full wave rectifier, transformer utilization factor is equal to 0.612. Next is bridge rectifier. The bridge rectifier is the most frequently used circuit for electronic DC power supplies. It does not need a center tap transformer. So this is the circuit diagram of bridge rectifier. It consists of 4 diodes D1, D2, D3 and D4 connected in the form of a bridge A, B, C, D. The 2 points A and C of the network are connected to the secondary coil, and the other 2 points B and D are connected to the load resistor RL. During the positive half cycle, the terminal A is positive with respect to C. So during the positive half cycle, terminal A is positive, and the diodes D1, so D1 and D3 will be forward biased. So during the positive half cycle, A is positive, so the current flow will be like this, that is, in this way the current flows. So D1 and D3 will be positive, that is forward biased, and D2 and D4 will be in the reverse biased condition. So D1 current flows in this way. And during the negative half cycle, terminal A is negative. So terminal A is negative means C is positive. So the current flow will be in this way. That is, D2 and D4 will be in the forward biased condition, and D1 and D3 will be reverse biased. So current will be flowing in this way. So that is, through the RL it will be in the same direction. So the output waveform will be like this. So in the first positive half cycle, D1 and D3 conducting, second D2 and D4 conducting. Next is peak inverse voltage. During the positive half cycle, diode D1 and D3 are conducting, and entire input peak voltage appears across the load resistor RL, and at this instant D2 and D4 are reverse biased. So peak inverse voltage is the maximum voltage across the non-conducting diode. So during the positive half cycle, the non-conducting diodes are D2 and D4, and the voltage across the non-conducting diode D2 is equal to the maximum voltage across the load resistor, and that is equal to Vm. Also across D4 is Vm. So we can say that the voltage across the non-conducting diode D2 or D4 is Vm. So the peak inverse voltage in the case of bridge rectifier is Vm. And the output DC voltage and current, the RMS value, that is VDC equal to Vm 2Vm by pi. Also IDC is 2Im by pi, and Vrms equal to Vm by root 2, IRMS equal to Im divided by root 2, and also the ripple factor gamma is equal to 0.482. That is, these factors are similar to the center tapped full wave rectifier. And transformer utilization factor is equal to 0.812 in the case of bridge rectifier. Let us compare the rectifier circuits. First one, number of diodes. So in half wave 1, full wave 2, bridge rectifier number of diodes is 4. Then peak inverse voltage is here Vm, then here 2Vm, bridge Vm. Then DC voltage, that is VDC is Vm divided by pi, here 2Vm divided by pi, here also 2Vm by pi. And DC current is Im by pi, here 2Im by pi, here also 2Im divided by pi. Then RMS voltage, here Vm divided by 2, here Vm divided by root 2, here also Vm divided by root 2. Then RMS current is Im by 2, here Im divided by root 2, here Im divided by root 2. Then ripple factor is 1.214 half wave, then 0.482 for full wave and bridge rectifier. Then efficiency is 40.6% for half wave, then 81.2% for both full wave and bridge rectifier. Then ripple frequency is F for half wave, then 2F for both full wave and bridge rectifier. Then transformer utilization factor is 0.287 for half wave, here 0.612, then here 0.812. So that is about the full wave rectifiers, that is center tapped full wave rectifier and bridge rectifier circuits. So thank you for watching the class. If you like the classes, please like, share and subscribe my channel.